All right, we're going to talk about section 11.3. There's two topics in this section. The first is going to be this idea of conditional probability, and the second is events involving the word and. So conditional probability. Sometimes the probability of an event B must be computed using the knowledge that some other event A has occurred. This type of probability is called conditional probability. And its notation is you'll see two letters, one denoting a particular event and the other a second event. And so you'll see a slash between them. This is conditional probability of B given A. That's how it reads. So the probability of B given A. So the key word to look for is given. Given means to reduce the sample space first to a smaller sample space and then calculate the probability. So we're going to take a look at some notation right now just to understand the differences. So we're going to use a sample space with numbers 1 through 20, and the event is to draw a single number at random. A is that we draw a number greater than 11, and the event B is that the number selected is odd. So A simply says find the probability of B. Well, that's just look at all 20 numbers and tell me how many are odd. Well, half of them are odd out of 20, so we get 1/2. Now the second one is this idea of and back from chapter 2 when we talked about set theory, we said that that meant both had to be satisfied. So this time we want to do A and B at the same time. So first we want to select a number greater than 11, and we want that number to also be odd. So a number greater than 11 that's odd is 13, 15, 17, and 19. So there are 4 numbers out of 20, or we reduce to 1/5. Now this notation is our new conditional notation that we're learning. So this is compute the probability of B given that A has already occurred. All right? So what that simply means to do is to create a new sample space. The new sample space has to be those numbers that satisfy A. So the only numbers that we can now have in our sample space are those greater than 11. So 12, 13, 14, 15, 16, 17, 18, 19, and 20. Now we want to look at, of these numbers in this sample space, which ones are odd. So 13, 15, 17, and 19 are odd, so we get 4. But remember, the denominator of a probability is how many are in our sample space. Well, we've had to create a new sample space because of this idea of given, and there are 9 numbers here, so 4/9. So let's stay with this idea of given and do a few more problems. So let's say that we have a club, and this club has Barry, Beth, Carol, Brittany, and Claire. What's the probability of selecting a female president given that the name starts with B? Every time you see this word given, it means create a new sample space. The new sample space you're creating are all of those people that satisfy what follows given. So the only people in our sample space are names that start with B. So Barry, Beth, Brittany. Now we do the probability that we get a female president. So in this list, there are 2 out of a total of 3. So when you do these given problems, you create a smaller sample space, and that's the only sample space you look at to compute your probability. Now, the sample space can change depending on what follows the word given. So find the probability of selecting a bee named President given that they are female. So now our new sample space is to write down just those names that represent female. So we would say Beth, Carol, Brittany, and Claire. And then we do the probability that it starts with a B. So we get 2/4 or 1/2. All right, now we're going to go to the second idea of 11.3, which are events involving and. So there's some key words we need to look for and some ideas that we need to address first. So if we want to find the probability of A and B, we can take the probability of A times the probability of B. But certain things have to be satisfied. First, key words to look for are this idea of both or the idea of all. Probability questions involving and require you to ask if the events are independent. Two events, A and B, are independent events if knowledge about the occurrence of one of them has no effect on the probability of the other one occurring. So let's just answer some questions here. Let's look at some scenarios and see if they're independent events. The probability of rain today and the probability of my garbage being collected today. Does one have any bearing on the other? No. If it rains today, the garbage will still be collected. So are these events independent? Yes. How about the probability of a severe hailstorm today and the probability that the local airport will be closed to flights sometime today? Those are not independent. If the weather is bad enough, the flights will be grounded and won't take off. So these are not independent events. So let's look at some examples. I think you're going to find that ideas in this section with and are pretty straightforward. So let's say we have an urn, and this urn contains a certain number of balls that are a certain color. Find the probability of selecting red on the first, green on the second, and then red on the third under the following conditions with replacement. That means you're going to draw out a marble or ball, and you're going to look at it, and you're going to put it back in the urn to draw again. Now, this is an and problem because it says the word and because you're drawing them one at a time. So the first one is we want the probability of red times the probability of green times the probability of red. So remember, an and problem is you compute the probability of each and you multiply them together. So what's the probability of red? That would be how many are red in the total number in the urn. So we would say 3/10 times, what's the probability of green? 2/10, because we put the ball back in the urn because it's with replacement, and we specifically want green, so we look at how many are green. And then red again is 3/10. Now we simply multiply these across and reduce. So we get 5/900, or if you prefer a decimal, 0.018. Now how does it change with replacement? Well, that's going to change your denominator number because every time you draw out a ball, the number in the urn will reduce. You might want to ask yourself, does it change the red that are left, since we have to pull red twice? So it's probability red times probability green times probability red. Well, the first draw is 3 red out of 10. The next draw is 2 green, because we didn't take a green one out, but out of 9, because we did not put the ball back in. And the next one is 2/8. The numerator is now 2 because a red was taken out and only 2 are left, and this is 8 because we're not putting them back. So you get 1/60th or 0.017. All right, a Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say they suffer great stress at least once a week. So this is the probability of person 1 times the probability of person 2 times the probability of person 3. Well, we want to calculate the probability that each of these people will suffer great stress. Well, they tell us that. They tell us the likelihood that any American suffering great stress at least once a week is 46%. So this is 0.46 times 0.46 times 0.46. And you get 0.097. Alright, so how about we switch to a deck of cards and we draw out a card one at a time and not replace it and find the probability of getting 3 jacks. Well, the probability of getting the first jack is 4 out of 52 times 3 out of 51 times 2 out of 50. Because you keep assuming you get a jack, so those lower by 1, and the denominator keeps lowering because you are not putting the card back. So you get 0.00018. How about an ace, king, queen in that order? Well, there's 4 ace out of 52. There's 4 king out of 51. There's 4 queen out of 50. This time, this number stays the same because these cards are all different. So you get 0.00048. The first card to be a diamond and the second card to be a heart. Well, there's 13 diamonds out of 52, and there's 13 hearts now out of 51. And you get 0.064. All right, so this next problem is going to look at the idea of given and the idea of and in 2 separate problems. So we're at a pet store with a certain number of cats. And here we go. We're selecting 1 cat at random. Mark selects a short hair given Mary selects a long hair. So remember what that means. That means that your new sample space has been reduced. So your new sample space is minus 1 long hair cat. So now you have 3 short hair, 1 long hair, and 1 Siamese. So the probability now that Mark selects a short hair is 3/5, not 3/6, because Mary took a cat home. Now what's the probability that they both select a short hair? Well, this is an and problem. So this is probability of short hair times probability of short hair. So the first probability would be 3 out of 6. Now the next one, a short hair has been taken home. So both of these numbers lower. This becomes 2 because there's 1 less short hair available for adoption, and the total is now 5. And so we get 1/5 as our answer. All right, let's look at a table and think about these ideas in a table. So what would be the probability that a student prefers to run? Well, I'd want to look at the running total over the total number of people in the table. So the running total is 28 out of 91 total people in the table, or 4/13. How about those who prefer yoga given that the student is male? Well, I'm only allowed to look at the males now because that's what this idea of given tells me. So I'm only allowed to look at these 53 people. So my denominator is 53 because I can only consider the males. Now, of the males, the numerator number is those that prefer yoga. So there's 20 that prefer yoga given that they're in the male category. How about those who prefer yoga and are male? Well, this means that out of the whole entire table, out of all 91 people surveyed, where sits the number that says these are those that are both male and prefer yoga? Well, it's this 20 because they fit in a box that satisfies yoga down and males across. So 20 out of 91. All right, so let 2 cards be dealt successively without replacement from a standard 52-card deck. Find the probability of drawing a club second given that a club was drawn first. Given does not mean that it's work for you to do. It means it's work already done that lowers your sample space. So now our new sample space is 51. It's minus a club. So now if we want to do this, if we want to draw another club, there's only 12 left because we know a club was removed. So there's 12 left out of 51 cards. How about what's the probability of getting all odd numbers if a die is rolled 4 times? This idea of all is the same as and. So you want the probability of odd times the probability of odd times the probability of odd times the probability of odd. Well, each roll is separate, so you always have 6 numbers on the die when you roll. So the denominator for all of these is 6. How many are odd? 3. So 3, 6, 3, 6, 3, 6, 3, 6. You could have also said 1/2 across all of there, and you get 1/16. All right, 2 women and 4 men are waiting to be interviewed for jobs. Find the probability that all the women will be interviewed first. All women first. So probability of all women first. So how many women are there? There's 2. So probability of woman first times probability of woman second. We do not need to have any men in this to compute because we're just worried about the probability that the women go first. Well, there are 6 total people being interviewed, so the probability that a woman would go first is 2/6 times another woman going is 1/5 because 1 has already gone, so that lowers how many are left, and it lowers how many in total are left for an interview. So you get 1/15 when you work that out. All right, 6 men and 7 women are waiting to be interviewed for jobs. If they are all selected in random order, find the probability that the first interview will be a woman and the remaining ones will alternate gender. All right, so the way that we're going to do this is there's 2 ways you can think about it. If you want to think about it like an and problem, the first woman and the remaining ones will alternate gender. Well, if the first one has to be a woman, you could say there are 7 women out of 13. Times all the rest have to alternate. So you can say here that there are 12 people left to go, and you're going to use a factorial, because what I'm doing here is I'm going to do all the alternating together. So there's 12 people left that have to alternate. So the bottom would be arranging 12 people. Now the top is that 6 men and 7 women then have to alternate. So it has to be man, woman, man, woman, man, woman. Right? So that means 6 factorial times 6 factorial, because you'd have 6 men, then 6 women, then you'd have 5 men, then 5 women, so on and so forth. When you come up with this answer, you get 0.00058. Another way to just simply do it all in one fraction is to say 13 factorial, and realize since there's more women than men, to have them alternate, a woman would really have to go first. So these could become together instead of separated, and 7 could just be absorbed here. You could do 7 factorial times 6 factorial, and you'd get the same answer.